So the next lesson is about the shapes that we can predict from our Lewis dot diagrams. So the shapes of molecules. The shapes of molecules are determined by the way the cloud of electrons are arranged around the central atom of the molecule. Remembering that electrons are negative and the bonds consist of electrons, so it's how these two negative zones kind of interact with each other, and that determines the shape of the molecule, because they will repel. Because since clouds of electrons are negatively charged, they will repel each other. So these two examples here of an animation, they're going to repel each other because they're both negative. So electron clouds. So remember in our last lesson we looked at sulfur dioxide. So electron clouds can be bonding or non-bonding. So obviously the ones that electron clouds are bonding are the bonds that are forming when electrons are being shared between atoms. So for example here, the sulfur and the oxygen. And the non-bonding is the electron pair above the sulfur, which is not involved in the chemical bonds. Okay, there's a diagram there. These are the bonding electron clouds there, and the non-bonding electron clouds are above the sulfur there. They're not involved in the bonds between the oxygen and the sulfur. There. Okay, so if there's one electron cloud, we call the shape linear, like carbon monoxide. A molecule containing only a single cloud of electrons must be linear, and the bond angle is 180 degrees. If you have two electron clouds, again, the only option you're going to have is going to be linear, even if it's got one lone pair or no lone pairs. And the bonding angle, again, because it's linear, is going to be 180 degrees. If you have three electron clouds, then there are more options. If you have two lone pairs, then you're going to get a linear molecule. And if you have one lone pair, it's going to be bent. An example being, of course, water, because the two lone, the non-bonding electron pair is going to push against the bonding pairs of the hydrogen and oxygen if it was water. And no lone pairs, it will be known as trigonal planar. And the bond angle this time is 120 degrees. Okay, so the bond angle here, 120 degrees. Here we go. If you have four electron clouds, then there are even more possibilities. If there are three lone pairs, then it will be known as linear, because you're going to have it so that the electron clouds are all trying to reduce the amount of interaction they have. If you have two lone pairs, it will be bent. If you have one lone pair, it will be trigonal pyramidal. And for no lone pairs, say for example like methane, it will be known as tetrahedral. Now notice tetrahedral and linear are very similar. In fact, they're all very similar, that they're going to, non-bonding and bonding pairs are all going to try and reduce the amount of interaction they have with each other. And these are the shapes that you're going to develop. In this case, the bond angle is going to be 109 degrees. Okay, so the final part of the lesson is about drawing tetrahedral and trigonal pyramids. So both these have bonds that, if you put it on a piece of paper, won't sit flat. So we've got to think in 3 dimensions. I suggest you, as we go through this video, you have a molecular model kit and work it out and through this particular slide by yourself. So they need to be drawn differently. So bonds in the plane of the page are drawn as sticks or lines. Okay. So they're going to go just up and down, okay, like that really, like an L shape. Okay. However, if the bonds are coming towards you or out of the page, these are drawn as wedges, so that means that it's poking towards you. And finally, bonds that are going away from you or behind the page are drawn as a dashed wedge. That's going into the page, as it were, because you're thinking in 3 dimensions. So that's enough for today's lesson about shapes. So again, I suggest getting some molecular model kits out, maybe in class, and working through seeing and drawing in 3 dimensions, especially around tetrahedral and trigonal pyramidal molecules and shapes.